Welcome to my 39th tutoring session in A-level chemistry. In this video, I'll explain how to draw the Lewis dot structures for atoms and molecules. Don't forget to subscribe my channel, share, like, comment, and watch the full video. Now, two things are important when you're trying to draw the Lewis dot structures for atoms and molecules. They are valence electrons and the elements symbol. Now, hydrogen atom has only one valence electron, and the valence electron of the hydrogen atom is present in the first shell. So hydrogen atom is having only one shell. And what about the elemental symbol for hydrogen? Now it is a capitalized one letter abbreviation for the hydrogen atom. And in case of helium, you find two valence electrons in the outermost shell. And what about the element symbol? So it is a two-letter abbreviation for the helium. And whenever the element symbol is a two-letter abbreviation, the first letter will be capitalized and this is followed by the second letter that is mentioned in the lowercase. And in case of lithium, you find a total of 3 electrons around the nucleus of the atom. The first shell contains 2 electrons and the outermost shell contains only 1 electron. So what is a valence electron? So valence electron is that electron which is present in the outermost shell of that particular atom. So in case of lithium atom, you find only one valence electron that is present in the outermost shell. And the symbol for lithium, it is a two-letter abbreviation with the first letter being capitalized followed by the second letter that is mentioned in the lower case. Now valence electrons are the bonding electrons that are present in the valence shell, that is in the outermost shell, while the core electrons are the inner shell electrons. Now here in case of lithium, you find two types of electrons, that is the inner shell electrons and the bonding valence electrons. Now the inner shell electrons are highlighted in green while the bonding electrons are highlighted in the violet color. So the core electrons or the inner shell electrons highlighted in green never show up in the Lewis dot structures. So inner shell electrons or the core electrons should never be considered for drawing the Lewis dot structures. So consider only the valence electrons for drawing the Lewis dot structures for any given element or a molecule. So in case of beryllium, you find a total of 4 electrons. 2 electrons are present in the first shell and the rest 2 electrons are present in the outermost shell, that is in the valence shell. The outermost shell is called the valence shell and the electrons present in the outermost shell are called valence electrons. Now again for beryllium, it is a two-letter abbreviation, that is the element symbol, where the first letter is capitalized followed by the second letter which is mentioned in the lowercase. And in case of boron, you find a total of 5 electrons, of which 2 electrons are present in the first shell, while the rest 3 bonding valence electrons are present in the second shell or in the outermost shell. And what about the element symbol? It is a one letter capitalized abbreviation for the boron element. Now Lewis dot structures for a particular given element is mentioned as dots around the element's symbol. So the valence electrons are represented as dots around the element's symbol. And that is how you draw the Lewis dot structure. So when you're trying to draw the Lewis dot structure for any given element, you represent the valence electrons as dots around the symbol of the element. Now there are two types of valence electrons, bonding electrons as well as non-bonding electrons. Both non-bonding and bonding electrons are present in the valence shell, while the core electrons are present in the inner shell electrons. So in case of carbon atom, you find a total of 6 electrons, of which 4 are the bonding electrons mentioned in violet color, while the inner shell electrons are mentioned in green. So in case of nitrogen, you find a total of 7 electrons, of which 2 are inner core electrons and the rest 5 are the valence electrons. Of these 5 valence electrons, 3 are the bonding electrons highlighted in violet color, while the rest 2 are non-bonding electrons highlighted in red. In case of oxygen, there are a total of 8 electrons, of which 2 are the inner shell or core electrons. The rest 6 are the bonding valence electrons. So the oxygen atom, there are a total of 6 valence electrons, of which 2 are bonding electrons and the rest 4 are non-bonding electrons. And in case of fluorine atom, there are a total of 7 valence electrons, of which only 1 is the bonding electron highlighted in violet color, while the rest 6 are the non-bonding electrons. So remember, it is the bonding valence electrons that participate in the chemical bonding process or in the chemical reactions. So the bonding electrons are highlighted in violet, while the non-bonding electrons are highlighted in red. So carbon has 4 bonding electrons, hydrogen has 1 bonding electron, nitrogen has 3 bonding electrons and 2 non-bonding electrons, oxygen has 2 bonding electrons and 4 non-bonding electrons, while fluorine has 1 bonding electron and 6 non-bonding electrons. So these are the 5 atoms that are regularly encountered in organic chemistry, that is carbon, hydrogen, nitrogen, oxygen and fluorine. So carbon, hydrogen, nitrogen and oxygen is fine. Now what about fluorine? So why is that I have included fluorine and I have mentioned it as a regularly encountered element in the organic chemistry? Is because nearly 25% of FDA approved drugs currently available in the market contain fluorine atom. And fluorine is the most electronegative element in the periodic table with a value of 4 on the Linus Pauling electronegativity scale. So carbon with 4 bonding valence electron, it bonds to 4 atoms. So in case of methane molecule, you can find carbon atom with 4 bonding electrons, it bonds to 4 hydrogen atoms. And in case of ammonia molecule, you find nitrogen atom with 3 bonding electrons, it is covalently bonded to 3 hydrogen atoms. And you find a lone pair of electron on the nitrogen atom, which is the non-bonding pair. So non-bonding electron is also called as lone pair of electron or unshared pair, because you don't find the lone pair participating in the chemical bonding process, or it doesn't share its electrons with other atoms. In case of oxygen atom, you find 2 bonding electrons and it covalently bonds to two hydrogen atoms in case of water molecule. And in case of fluorine atom, you find only one bonding electron. It covalently bonds to hydrogen atom, resulting in formation of hydrogen fluoride molecule. So the valence electrons are of two types. One is the bonding type, the other is the non-bonding type. So bonding type, they participate in the chemical bonding process and they are highlighted in violet color, while the non-bonding electrons are highlighted in red color. So remember, a covalent bond is formed by mutual sharing of one pair of electron shown by a solid line, while a double bond is formed by mutual sharing of two pairs of electrons between the atoms involved in the bonding process. Like in case of carbon dioxide molecule, you find two double bonds between the central carbon atom and the terminal oxygen atoms. And a triple bond is formed by mutual sharing of three pairs of electrons between the atoms involved in the chemical bonding process. Like in case of nitrogen molecule, you find a triple bond between two nitrogen atoms. So a single bond is formed by mutual sharing of one pair of electron. A double bond is formed by mutual sharing of two pairs of electrons, while a triple bond is formed by mutual sharing of three pairs of electrons between the atoms involved in the chemical bonding process. Now let me explain the rules for drawing the Lewis dot structures with respect to water, carbon dioxide and nitrogen molecule. Rule number 1, count the total number of valence electrons. Now first and foremost, you have to count the total number of valence electrons for all the atoms in the molecule, and then you add up the valence electrons for all the atoms in the molecule. Let me explain with respect to the water molecule. So molecular formula for water is H2O, where oxygen atom is covalently bonded to two hydrogen atoms, shown by two solid lines joining the oxygen atom and the two hydrogen atoms. So in the water molecule, you find one oxygen atom that is covalently bonded to two hydrogen atoms. So oxygen atom, as I've already explained, it has 6 valence electrons. Hydrogen atom has only one valence electron. Now you have to add up all the valence electrons present in all the atoms in the molecule. So oxygen has 6 valence electrons, hydrogen has 1 valence electron. So there are two hydrogen atoms, that will be 1 plus 1. So total number of valence electrons will be 6 for oxygen, 1 for hydrogen, and it will be total of 8 valence electrons. So 8 valence electrons are present in the water molecule. So now we have to arrange the atoms around the central atom. Now usually the central atom will be the least electronegative atom. But here in case of water molecule, you find the oxygen atom is the central atom, while the hydrogen atom is the terminal atom. So this is an exception. So hydrogen is always a terminal or outside atom. So whenever hydrogen atom is part of the molecule, it will be always present as a outside atom or a terminal atom. So only in the absence of hydrogen atom, the least electronegative atom will always be the central atom. So hydrogen will always be the outside or the terminal atom. So in case of water molecule, oxygen atom is the central atom, and because hydrogen atom is also part of the molecule, it will always be the outside or the terminal atom. So oxygen atom is the central atom and hydrogen atom will be the outside or the terminal atom. And make sure that the octet is complete for the atoms. So octet for most of the atoms, and for hydrogen it will be duet. So octet for most of the atoms and duet for hydrogen atom, because hydrogen atom cannot accommodate more than 2 electrons in its outermost shell. And now we have to draw the single bonds. So I can draw the single bonds, and this can be shown by a solid line joining the central atom and the outside atoms. Or you can also mention the single bond by means of a pair of dots between the central atom and the outside atom. So here you can see, in case of water molecule, a bond is drawn and is shown as a solid line joining the central oxygen atom and the outside hydrogen atom, and can also be shown as pair of dots between the central oxygen atom and the outside hydrogen atom. And remember, each single bond accounts for 2 valence electrons. So here you find 2 bonds between the oxygen atom and the hydrogen atoms, and therefore you have used up 4 electrons out of a total of 8 valence electrons. So remember, there are 8 valence electrons in the water molecule, of which right now we have used 4 electrons, and we are left with 4 more valence electrons. So what do we do with the remaining 4 electrons? You have to distribute the remaining valence electrons. And when you're trying to distribute the remaining valence electrons, always start with the outside atom and then come to the central atom. Now, as I've already mentioned, hydrogen atom cannot accommodate more than 2 electrons in its outermost shell. So, duet for hydrogen and octet for rest of the atoms. Here you see that duet is complete for both the terminal hydrogen atoms. And what about the central oxygen atom? So you find that central oxygen atom has only 4 electrons. So it is short of 4 electrons now. So in order for the central oxygen atom to complete the octet, oxygen atom needs 4 more electrons. And we are left with 4 more electrons. So what you do? You convert the rest of the 4 electrons into 2 lone pairs on the oxygen atom. And now you can see that octet is complete for the central oxygen atom and duet is complete for the terminal hydrogen atoms. The next step, you form multiple bonds if necessary. So it is not that you have to mention only single bonds between the atoms in the molecule. You can even form multiple bonds like double bond and triple bond. So in case of carbon dioxide molecule, you see that the least electronegative carbon is the central atom and the electronegative oxygen atom is the terminal or the outside atoms. And here you find both the terminal or outside oxygen atoms. It has an octet. So octet is complete for the outside oxygen atoms. So both the outside oxygen atoms have a set of 8 electrons. Octet is complete. So what about the central carbon atom? The carbon atom has only 4 electrons. So it is short of 4 electrons. So what do you do? So when the central atom is short of electrons, you can always feel free to convert the lone pairs on the terminal atoms into bonding pairs. So here I convert one of the lone pairs on the terminal oxygen atom into bonding pairs between carbon and oxygen atom. And I repeat the same. I convert the lone pair on the other terminal oxygen atom into bonding pair between the oxygen atom and the carbon atom. And now I see that octet is complete both for the central carbon atom as well as for both the terminal oxygen atoms. And what about nitrogen molecule? So nitrogen, so what is the valency of nitrogen? So nitrogen has total of 5 valence electrons. So in case of nitrogen molecule, you find 2 nitrogen atoms, so that will be 5 plus 5. So when you count the total number of valence electrons in nitrogen molecule, that will be 5 plus 5. 5 valence electrons for each nitrogen atom. That will be total of 10 valence electrons. So here you find a total of 10 valence electrons, but you see that the octet is not complete. So whenever the octet is not complete and whenever the atom does not have a octet, what you can do is you can convert the lone pair of electrons on the atom into bonding pairs between the atoms. So I convert one of the lone pairs into bonding pairs, and now I see that only one nitrogen atom is satisfied with octet, while the other has 6 electrons. So in order to complete the octet for the other nitrogen atom, what I do, I repeat the same process. I convert the lone pair into bonding pair, and now I see that both the nitrogen atoms have a set of 8 electrons. So octet is complete for both the nitrogen atoms, and I form a triple bond between the two nitrogen atoms. So whenever the octet is not complete, you can always feel free to convert the lone pairs on the terminal atoms into bonding pairs between the atoms, and then form multiple bonds, which could be either double bond as in case of carbon dioxide molecule, or it could be a triple bond as in case of nitrogen molecule. And finally, check the structure. Verify the total number of valence electrons used matches the initial count, and ensure that all atoms have the appropriate number of electrons. So octet, so make sure that octet is complete for the atoms and duet for hydrogen. So for example, in case of water molecule, you see that duet is complete for the two terminal hydrogen atoms and octet is complete for the central oxygen atom. So these 6 steps are only for neutral molecules. So what about if the molecule is charged, like in case of ammonium ion and cyanide ion? So for polyatomic ions, so what you have to do, you add 1 electron for negative charges and subtract electrons for positive charges. So whenever you find negative charges in a polyatomic ion, you add electron, that is 1 electron, and subtract electrons for positively charged polyatomic ion. For example, in case of ammonium ion, so total number of valence electrons will be, so what about the valence electrons for nitrogen? Nitrogen it is 5. And what about hydrogen? Hydrogen it is 1. So there are 4 hydrogen atoms covalently bonded to nitrogen atom. So that will be 4 electrons. So 5 plus 4. So since ammonium ion is a positively charged ion, you subtract by 1. So 5 plus 4 minus 1, that will be 8. So total number of valence electrons in case of positively charged ammonium ion will be 8. And what about the negatively charged ion, cyanide ion? So valency of carbon is 4 plus what about nitrogen? 5. And since it is a negatively charged ion, that is cyanide ion, you add up 1 electron. So 4 plus 5 plus 1 is equal to 10. So there will be a total of 10 electrons in the cyanide ion. And you can just cross check it. Finally, you can count the number of electrons. So it is, so 3 bonds will be 6 electrons, 2 electrons on carbon and 2 electrons on nitrogen. So that will be 6 plus 2 plus 2, that will be 10. And always first mention the bracket and then mention the charge. So first mention the bracket and then mention the charge, and this charge should be superscripted. And now I believe you're all set for drawing the Lewis dot structures for any given atom or molecule. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.